is Anita, and in this video I am going to discuss about AC circuit analysis for series RLC circuit. Now, just for understanding this, let us make the power circuit diagram. So when I am going to make the power circuit diagram for this, means I need to make a AC source which is represented by this symbol, and mathematically I can write Vm sine omega t, and this is feeding to a series R, L and C circuit. So R is resistance, L is inductance and C is capacitance, and here the current IT is there. Now in case of series connection, we know voltage adds. In case of series connection, voltage adds. Okay. Now, if the voltage across VR is V, voltage across R is VR, voltage across L is VL, and voltage across C is VC, then the supply voltage VT is equal to, I can write VR plus JVL minus JVC. Now, you will be surprising that why I am not directly adding it, why I am multiplying this by J with VL, and why I have multiplied minus J with VC, and after I have added it. So for that, you need to understand that in case of resistance, inductance and capacitance, when we were studying the pure resistance circuit, I have already told you that the voltage and the current are in same phase. Okay. And what is voltage across resistor? Voltage across resistor is I into R. That means R is a directionless quantity and current is a direction quantity. That means the multiplication of I and R will be in same phase with I. So you can see here that VR is in same phase with I, and its magnitude is more than I. We are going to get it VR after multiplication of I and R. Now, similarly for inductance, we have seen the current lags from the voltage by 90 degrees. Now, you can see here that voltage across inductor will be in same phase with the I, because voltage across inductor will be I into XL. So, if I am going to make VL, that will be in same phase with the current. Similarly, in case of capacitance, we know that VC is equal to I into XC. So if this is V, this is I will be 90 degree lead from the voltage. So you can see here that VC will also be in same phase with IC. That means VC will also be lead 90 degree from the voltage. Now you can see VR is same phase with V. VL is 90 degree lagging from V, and VC is 90 degree leading from voltage V. So that means if I am going to add this VL and VC along with V means VR. Okay. So if I'm going to add this V, I need to rotate VC 90 degree in anti-clockwise clockwise direction and VL 90 degree in anti-clockwise direction. So VL basically, what is JVL? JVL means we are rotating the vector VL by a 90 degree in anti-clockwise direction. So J, and similarly VC minus JVC means we are rotating a vector VC in a clockwise direction by 90 degrees. So basically what J is representing, the J is nothing but it is showing the rotation of 90 degree in anti-clockwise direction, and minus J is showing the representation of rotation of vector VC in 90 degree clockwise direction. So that's why this plus J and minus J are coming into picture. Now, after putting the value of Vt, that is Vm sine omega t, VR I can write It into R. J, VL I can write It into XL. And minus J, Vc I can write It into XL. That is It into R plus J, It into XL minus J, It into XL is inductive reactance, and XC is capacitive reactance. Now, if I further solve it, I can take IT common. I am going to get R plus JXL minus JXC, that is equal to Vm sine omega t. Now from here, if I want to calculate IT, so that is Vm upon R plus JXL minus JXC sine omega t. This further always IT is equal to Vm upon R plus J, I can take common, XL minus XC sine omega t. Now again, this is a complex number and I can represent it by its polar number, that I can write it as Vmz angle phi sine omega t, where Z is equal to under root R square plus XL minus XC ka whole square. And what is phi? Phi is equal to tan inverse. So phi is equal to tan inverse XL minus XC by R. So this is how I can convert the polar number from its complexity. Now further I can Vm by Z sine omega t plus minus phi. Now what is plus minus phi? Because if XL is greater than XC, the value of phi will be positive. If XL is less than XC, the value of phi will be negative. So if XL is greater than XC, then phi will be positive. XL is less than XC, then phi will be coming negative. Okay. And if XL is equal to XC, then phi will be 0. Okay. So if phi is positive, then if I'm going to take it in numerator, it will be negative sign. If phi is negative, if I'm going to take in numerator, it will be positive sign. So that's why the both symbols have been written, because it depends on whether it is coming positive or negative. It depends on the value of XL and XC. So finally, you can see here that Vt is equal to Vm sine omega t, and It I'm going to get Im sine omega t plus minus It is equal to Im sine omega t plus minus phi. So you can see here that the phase angle in case of phase angle, so you can see that phase angle in case of series RL circuit, phase angle in case of series RLC circuit, circuit will be plus minus phi. That means it can lag also, it can lead also, depending on the value of XL and XC. Now coming to its phasor diagram. If I will make the phasor diagram for this phasor diagram, so phasor diagram, it can be, see, there are three cases. Case number 1, when XL is equal to XC. Case number 2, when XL is greater than XC. And case number 3, when XL is less than XC. So when this case is there, when XL is equal to XC, that means the behavior of the circuit will be resistance and the phase angle will be 0. So this will be the phasor diagram. If XL is greater than XC, that means ultimately the behavior of the circuit will be as per the inductance. So you can see here, current will lag by angle phi. See, when XL is equal to XC means tan inverse XL minus XC by R. This will be the value of phi. So since XL minus XC is 0, means tan inverse 0 by R. मतलब angle क्या हो गया? 0. Now similarly, if XL is greater than XC, then you can see phi is equal to tan inverse XL minus XC by R. So I am going to get tan inverse, okay, tan inverse XL minus XC. मतलब it is, this difference is going to come positive. So suppose that value is coming, that the difference of this is coming, that is suppose it is coming A by R. What is A? A is nothing but it is the difference of XL minus XC. So you can see here phi I am going to get the positive value. Whereas if XL is less than XC, so what I am going to get? Phi is equal to tan inverse XL minus XC by R. So this comes negative. So that means phi is coming negative. So what phasor So what is the phasor diagram? Phasor diagram will be V here and I will be leading by an angle of phi because phi is coming negative, means current will lead from voltage. Okay? So there are three cases possible. There are three cases. So three cases are possible. Case one, when XL is equal to XC, then this will be the phasor diagram. XL is greater than XC, this will be the phasor diagram. And XL is less than XC, this will be the phasor diagram. Okay. And if I want to make the general phasor diagram, so if I want to make it net phasor diagram, so this is V, this is VR, this is R, here VC, here VL. Okay. I hope you understand the series RLC circuit analysis. Keep watching my video. In next video, I am going to discuss about a very important phenomenon in series RLC circuit, that is a series resonance.